All right, guys. So last chapter we talked about sinusoidal systems, and in particular, we took a look at various techniques in which you can actually analyze circuits that are undergoing what we call sinusoidal steady state. Now, in this chapter, we want to turn our attention not to techniques of circuit analysis in terms of finding voltages and currents and things like that. We really want to talk a little bit more about power systems. And we're going to begin with the definition of instantaneous power. Right? So here, let's talk about instantaneous power. Suppose that you have a circuit element like this, and we place a voltage across the terminals, and there's a current that goes in through one of the terminals, through the circuit element, and then out of the terminal. We know that the power associated with the circuit element, which is a function of time, can be computed according to the passive sign convention as the product of the voltage times the current. Now, the type of power that we want to deal with is sinusoidal steady state power. So both the voltage and the current in general can take on the following forms. So for sinusoidal steady state systems, one of the things that we can say is that the voltage as a function of time, it has some amplitude, and it's going to be with the cosine reference, the cosine of the angular frequency times time, plus some phase constant associated with the voltage. Similarly, one of the things that we can also say is that the current as a function of time, again for these sinusoidal steady state systems, it's going to have the same angular frequency as that of the voltage. The amplitudes are going to be different, and in general, the phase angles are going to be different as well. Based on this, it's a relatively straightforward matter to calculate the instantaneous power by taking both of these and plugging them directly into this. So for these types of systems, the power associated with them, well, it's the voltage magnitude times the current magnitude times the cosine of omega t plus the phase angle for the voltage times cosine of omega t plus the phase angle for the current. Now, from a theoretical point of view, this is it, right? We don't need any extra information. However, the form of this equation right here really doesn't lend itself to very good interpretation. So one of the things that we want to do in this section is we want to use various trig identities along with a few definitions to manipulate this in such a way that the final form, equivalent form for the power, various components of the power can actually be further investigated and more well understood, right? And the place where I'm actually going to begin in this equation, in order to turn it into one that we can interpret more easily, is I'm going to begin with a trig identity. And the trig identity tells us that the cosine of the sum of two angles, or I'm sorry, the cosine of the product of two angles like this can be rewritten as cosine 1/2 alpha minus beta plus cosine 1/2 cosine of alpha plus beta like this. And what I'm going to do is, I'll call this up here equation 1, I'm actually going to let, in the trig identity, I'm going to let alpha be omega t plus the angle, phase angle for the voltage, and beta be omega t plus the phase angle for the current, right? Keep in mind that the analysis that I'm going to undergo right now is slightly different than what's actually done in the textbook. However, the conclusions are going to be absolutely identical. So I'm trying to give you at least a slight different point of view and show you that you can actually attack various problems from different angles here. Now, if I form alpha minus beta, notice that what I'm doing here is I'm subtracting these two. And these terms right here completely cancel out, and we're left with the phase angle of the voltage minus the phase angle of the current. Similarly, if I take alpha plus beta, then notice that this term and that term double up, and we're left with 2 omega t plus theta v theta I. And I can actually use this in the trig identity. So equation 1 can be rewritten in the following manner. The power as a function of time is equal to the magnitude of the voltage, the magnitude of the current, and then it is 1/2 of cosine alpha minus beta, which we just found to be theta v minus theta I, plus 1/2 the cosine of alpha plus beta, which we just found to be 2 omega t plus theta v plus theta I. Notice that this also distributes very easily and can be rewritten in the following manner. So here I'm distributing these terms, and I'm left with this. Now, this term right here, I'm going to leave in its final form. So this is going to be left. One thing that I really want to emphasize here is the fact that this term itself, even though it's kind of a complicated term, notice that it has 0 time dependence. There is no time there. All of the time dependence in the power is right there. And this is actually going to have consequences when it comes to how power is actually delivered and how it's absorbed by various components in your circuit. I also want to now focus on this second term. And I'm also going to use a trig identity in order to really kind of rewrite it in a better fashion. The new trig identity that I'm going to use is now that the cosine of two angles, alpha plus beta, is now cosine alpha cosine beta minus sine alpha sine beta. And we're going to choose alpha to be the constant term, right? So notice that this term right here contains no time dependence. Well, we're going to choose the beta term to be the one that carries the time dependence. So here it is that term right there. Now with this, one of the things that we can do, and we're almost at the end here, is this term that we have here, we can actually split into two parts. So the power can be rewritten as v sub m times e sub I divided by 2 times the cosine of the phase angles of the voltage and the current split apart. We have another term, v sub m times v sub I over 2 times the cosine of theta v minus theta I times the cosine of 2 omega t. And then lastly, minus v sub m I sub m over 2 times the sine of theta v minus theta I times the sine of 2 omega t. So these two terms here came about from splitting this one up by using this particular trig identity. This is what I wanted to get to. This is another equivalent way of computing power for sinusoidal systems. In the next section, what we're going to do is we're going to concentrate on each one of those terms separately because they each have a separate interpretation as to what is actually going on in terms of the power being either absorbed or delivered by our system.